Relativistic baseball. What would happen if you tried to hit a baseball pitched at 90% of the speed of light? The answer turns out to be a lot of things, and they all happen very quickly, and it doesn't end well for the batter or the pitcher. I sat down with some physics books, a Nolan Ryan action figure, and a bunch of videotapes of nuclear tests and tried to sort it all out. What follows is my best guess at a nanosecond by nanosecond portrait. The ball would be going so fast that everything else would be practically stationary. Even the molecules in the air are effectively standing still. Air molecules would vibrate back and forth at a few hundred miles per hour, but a ball would be traveling through them at 600 million miles per hour. This means that as far as the ball is concerned, they would just be hanging there, frozen. The ideas of aerodynamics simply wouldn't apply here. Normally, air would flow around anything moving through it, but the air molecules in front of this ball wouldn't have time to be jostled out of the way. The ball would smack into them so hard the atoms in the air molecules would actually fuse with the atoms in the ball's surface. Each collision would release a bunch of gamma rays that scattered particles. A thin fusion zone forms in the front of the baseball, as nitrogen and oxygen from the air fuse with the carbon, hydrogen, and nitrogen in the ball, with a near vacuum left in its wake. The gamma rays and debris would expand in an outward bubble centered on the pitcher's mound. They would start to tear apart the molecules in the air, ripping electrons from the nuclei and turning the air in the stadium into an expanding bubble of incandescent plasma. The wall of this bubble would approach the batter about the speed of light, only slightly ahead of the ball itself. The constant fusion at the front of the ball would push back on it, slowing it down, as if the ball were a rocket flying tail first while firing its engines. Unfortunately, the ball is going so fast that even the tremendous force from this ongoing thermonuclear explosion would barely slow it down at all. It would, however, start to eat away at the surface, blasting tiny fragments of the ball in all directions. These fragments would be going so fast when they hit air molecules they would trigger 2 or 3 more rounds of fusion each. After about 70 nanoseconds, the ball would arrive at home plate. The batter wouldn't have even seen the pitcher let go of the ball, since the light carrying that information would arrive at about the same time the ball would. Collisions with the air would have eaten the ball away almost completely, and it would now be a bullet-shaped cloud of expanding plasma, mainly carbon, oxygen, hydrogen, and nitrogen, ramming into the air and triggering more fusion as it went. The shell of X-rays would hit the batter first, and a handful of nanoseconds later, the debris cloud would hit. When it reached home plate, the center of the cloud would still be moving at an appreciable fraction of the speed of light. It would hit the bat first, but then the batter, plate, and catcher would all be scooped up and carried backwards through the backstop as they disintegrated. The shell of X-rays and superheated plasma would expand outward and upward, swallowing the backstop, both teams, the stands, and the surrounding neighborhood, all in the first microsecond. Suppose you're watching from a hilltop outside the city. The first thing you would see is a blinding light, far outshining the sun. This would gradually fade over the course of a few seconds, and a growing fireball would rise into a mushroom cloud. Then, with a great roar, the blast wave would arrive, tearing up trees and shredding houses. Everything within roughly a mile of the park would be leveled, and a firestorm would engulf the surrounding city. The baseball diamond, now a sizable crater, would be centered a few hundred feet behind the former location of the backstop. Major League Baseball Rule 6.08b suggests that in this situation, the batter would be considered hit by the pitch and eligible to advance to whatever remains of the first base. After I initially published this article, MIT physicist Hans Richardsnet contacted me to say he'd simulated this scenario on their lab's computers. He found that early in the ball's flights, most of the air molecules were actually moving too quickly to cause fusion and would pass right through the ball, heating it more slowly and uniformly than my original article described.